Welcome everyone. My name is Jay Surya and the topic of this presentation is weak heaps. This is my first presentation for design and analysis of algorithms for fall 22. Let's first look at the history of weak heaps. This presentation is based upon a paper written by Dr. Ronald Dutton, who was a faculty at UCF, and his paper was titled Weak Heap Sort, and it was published in the year 1993. So let us look at the definition of a weak heap. A weak heap is formally defined as a binary tree where the root has no left subtree, and the second rule is that a given node is always equal to or greater than all of its right children. And in the third rule, this states that nodes having fewer than two children, except the root, appear only on the bottom two levels of the tree. This has to do with balancing the tree. So let us look at all these three rules with an example. So looking at this heap, uh, the root node has a value of 55, and this root node has a value greater than any other node in its right subtree. And as we've seen in the first rule, the root node has no left subtree. So coming to the right side, the node with value 42, in this node, uh, the value is greater than any node in the right subtree, and we do not need to take into account the value of the left subtree. And with in accordance to the third rule, nodes with two or lesser children are in the last two levels of the heap. And as you can see, the right subtree and the root node, which is the node with the value 42, creates a separate heap in which no value is greater than 42 in its right subtree. So now let us look at the differences between a heap and a weak heap. So weak heaps do not require the leaf nodes on the bottom level to be as far to the left as possible, as is the case in a normal heap. A weak heap is simply an extension of the heap dataset, and it involves relaxing the requirements of a heap, which leads to improved performance. And there is no relationship between the value of a node and its left subtree values, as we have already seen in the previous rules. So let us see how a weak heap is represented in the memory. So a weak heap can be represented using a one-dimensional array, and a weak heap with n nodes can be represented in an array of size n plus 1. So looking at the indexing of all the values, the left child of an index I is at index 2I, and the right child of an index I is at the location with index 2I plus 1. As you can see, uh, uh, taking I as 1, 2I gives the value of index 2, which is the left child, and 2I plus 1 gives the value of 3, which is the right child. And this is the array representation of this particular given big heap. Moving on, uh, merging is one of the most important functions of a weak heap. This merging again comes back when we will look at the weak heap sort function. So here we have two weak heaps, H1 and H2, and within this, the root value of the node with a value of 90 is larger than 80. So we pick this root value of 90 to be the root for the merged weak heap. And after that, H2 is appended to the node 90 as the right child, as we have already seen that the root node has no left childs. and then the remaining nodes of the H1 is appended to the child of the root node as the left child. So this becomes the left subtree of the node 80. And one of the most peculiar functions of the heap sort, of the weak heap, is called reverse bits. So reverse bits used to used to indicate if a node is a left or a right child. When we use the merge function, the left child and right child becomes switched in some cases, and a Boolean array called reverse bits is used to keep track of this. So, as you can see with the previous example, uh, uh, the node with the value 80 is given a false bit. So this means that 80 is at an index of 1, and the value at the node at index 2i is the left subchild of 80. So in this case, 2i gives the index 2, which is 70, which you can see here is the left subchild of the node 80, and so on goes. So, coming to the main topic of this presentation, which is the weak heap sort. Weak heaps can be used to sort a given array of integers or numbers. So, the first step is to build a weak heap out of all the elements of the array. And when the root is repeatedly exchanged with the last element of the array, which is shifted down to its proper place. And for step two, the heap is checked if it's empty, and then the root is removed, resulting and the resulting two weak heaps are merged. And for step two is repeated until we get the sorted array. So this might sound a little vague and complicated, but we can see this with an example. And before that, let me show you the weak sort algorithms. And this is the pseudocode for this entire weak heap sort. So the function weak heap sort encompasses the entire process, and the merge function is just the function we saw recently, and the function merge for us calls this function recursively, and until the heap is sorted entirely. And let us see with an example. So here is an example of a weak heap, and first we take the root node and insert it into the end of the array. As we have seen the property that the root node is the largest value in the weak heap, and so our array has the value 60 at the end. And after this, the weak heap is split into two separate heaps. So So these are the resulting two heaps, and we use the merge function which we saw recently, and the value 55 is the highest in this between these two, so that is taken as the root node, and the right subtree is taken as this second heap, and we obtain this weak heap. So again, we take the root node, which is the largest node in this particular weak heap, and we push it into this array at the end, and we continue this process all over again. So again, we obtain two sort. So the two separate trees are merged again using the merge function, and from this we have the value 55 as the value 50 as the largest node, and that becomes the root node, and this is removed and moved into the array, and this is the array at the end of step 3, and we continue this process again between these two trees, and 45 being the largest value becomes the root node, and it is moved into the array, and it is split into two different trees having 40 as the largest value, and in this case 40 is the largest value, and is the root of this weak heap, and it is pushed into the array, and at the end we are left with two elements 30 and 20, which are split and added into the array, giving us the final sorted array, which is in ascending order. And the benefits of using a weak heap sort over a normal heap sort is that it performs less number of element comparisons when compared to heap sort, and this in turn makes the time complexity and space complexity of this weak heap sort lesser than the normal heap sort. And the worst case scenario of weak heap sort is n log n plus 0 0.1 n. So all the branch swapping can be done within the array, and this can be done using the reverse bits, which is a trait unique to the weak heap data structure. And sorting can be done in place by just using one array, as it has n plus one number of as the size of the array we use to represent it is n plus 1, so no extra array is required to take this. So that is it with regards to this. Thank you for listening to my presentation.